Okay, so hello again. This is Francis Orozco, and this is the continuation of our problem solving for the mock problem set for the National Olympiad on Informatics. So in the last video, we've answered the third problem, alien defense. So this is just some sort of a geometry problem, okay, for those of you who are reviewing. So let's go back to the problem set. So for the next one, okay, we'll be solving Bob's prob. Okay, so essentially, if we are going to deduce these types of problems, okay, this is nothing but a change for a dollar. Okay, wherein the currency, it's some sort of a unique way called K dollar. So we have K to the $0 and K to the $1, and so on and so forth. Let's say if k is equal to 3, we have the denominations 3 raised to the 0 or 1, 3 raised to the 1 or 3. So we have the denominations 139 dollar. Okay, so essentially, if we have an input, let's say 12.3, so for $12, it it can go 7 ways. So the following ones are enumerated. And we have a limitation that n and k is less than or equal to 1 million. Okay, again, it's 1 million. So if ever that the number of ways exceeds 10 to the 9, 1 billion, okay, we should print our result modulo 1 billion. Okay. So first one, actually I tried solving this problem, okay, by the use of the change for a dollar algorithm. Uh, okay, so if you uh, Rosetta Code has an algorithm for that. Okay, although they have in Java, this is real slow as far as I know. Okay, the the algorithm that I used was the iterative part of JavaScript. So essentially, I made a port for that. Okay, so we have solution. Oh, we just need a class, not a project solution. Okay. Okay. So first, we have to have the function count once. Submit static. So since we are dealing with large numbers here, I use big integer. Okay. The number of this is 10, and these are the array of the denominations. Okay. As specified in in the Rosetta code. So next, we have a new array here of length, the value. Okay, so if we are to have 12 as the value of n, okay, of n, okay, plus 1. Okay, so we consider the value of 0. Okay, in this case. Okay. 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 Things fine. So we have t of 0. Let's initialize it to 1. Okay, So in big integer, we use methods and constants, okay, for this case. So next, we initialize the whole array by 0. So let's put 1 ctr, okay, it's less than length, okay, ctr is equal to the big integer of 0. Okay, we initialize the array to 0. Next, we do some magical stuff as shown in Rosetta code. So we have two arrays. A, okay, so the first for loop denotes the number of passes. So it is dependent on the number of denominations. So going back to our example, if n is 12 and k is 3, we have three denominations that is less than or equal to 12, which is 1, 3, and 9. Okay. And then for the second array, this is just iterating from 1 up to n. Okay. So if current value of 1 to n, okay, is greater than that of the currency, increase the, so p of b is equal to p of b plus, so we use add, okay, current value minus the current currency, okay, current index minus the current currency. Is this okay? Oh. The index of the current value minus the value of the current currency. Okay. Next, we have a return value here. And then we perform a modulo. If we want a constant that is not 1, 0, or 10, we have to do it as a string. So we have 1 billion, thousand, million, billion. Okay. So we have code the main. Okay. Next one. We have the denominations. Okay. So for values, if n is 12 and k is 3, the denomination should be 1, 0, 1, 3, and 9. Okay. So in essence, we say that 3, the largest value that we can have as an exponent is 2, wherein 3 raised to 2, we are guaranteed that this is the largest that is less than or equal to 12. Okay, so how do we do that? First, the base. Okay, in the base raised to the exponent is your number. Okay, so by the laws of logarithms, the exponent is just the log of the number divided by the log of the base. Okay, so we have the log of the number divided by the log of the base. So we have math, mm-hmm, new integer. Okay, so we have, so the number of elements of the our denomination should be math log of n divided by math log k. Okay, and then we would round up. Okay, so this is a double. So in Java we have to typecast this one and then add one. Okay, is this correct? Hmm. Is this one correct? Okay, so we have int. Oh, sorry. Okay, so next for int ctr is equal to 0, ctr is less than denomination dot length is for ctr, denomination of ctr is equal to math dot. So this is just base and the exponent, right? For encounter, but this is in double, so we have to typecast it as integer. And then we have system that outs program increments and denominator. Okay, so next we run the program. Okay, so it's 7. Okay, so we copy it and let's see how it goes. Okay, okay, our one and only test case pass. How about the judges test cases? Okay, okay, okay. So if we run in Java, okay, out of the 64 test cases, we only got 59, and the for 5 test cases, term we have Uh, okay, it's considered wrong because it exceeded the 4-second limit. Okay, so that's for Java. So my solution, okay, my solution is to do it in C. Okay, so C. Oh, okay, so let's do this one in C. Okay, so first we include, okay, so diode.h. Okay, and then we have inf min. Working in Notepad is really different than Eclipse because don't have autocomplete and 0. Okay, so next in C we have to declare the variables nk, and in C it's just a simple scan f%, %d. Okay, nk. Next we have to declare the array denomination. So we have the num, having what? It should be, okay, math.log of n divided by math.log of k. Okay, so we have log of n divided by log of k. Okay, but this one is of uh, type double, so we have to cast it again as integer, and then we add 1 to it. Okay, next we have to insert the values of the denomination. Okay, so we have declare first the variable, so that's the C style of coding. Okay, problem is how do we get the length of the array? So we have okay, we do some pointer technique. And then we have power, right? Base and exponent. So this is double, so we have to typecast it as int. And then printf percent d dash n, okay, of count points which we will implement. So this is n, and this is the array of denominations. We also have to pass the size because this, okay, inside the function doesn't work. Okay, so let's implement the count points. Okay, actually, since the value is 1 trillion, actually in C there's this data type called long, okay, which can handle that. So our formatter is LLD, okay, a long integer. Not not to be confused with long int. There's long int in C. Oh, I forgot. Let's include the math function for pow and log. So we have long const. In Java, we do this. In C, this is the style of coding, right? Size. Okay. I'm really confused because in Eclipse, whenever you type this automatically appears, but whenever you type this, you have to still type this. Anyway, it's just a matter of preference. So we declare our array. Then this is the C style. Declare variables first. Okay, initialize it to 1. Okay, this is how we use long. We append ll for the constant, or for the value rather, if we ever initialize a value. Okay, so next, in C, we are not guaranteed that whenever we have an array, its values is equal to 0, so we have to initialize it, or set it rather. Okay. Next we have two loops, a is equal to 0, a is less than the size, it's a, b is equal to 1, for b is equal to 1, is less than. Okay. P of b is equal to, okay, we can do this, p of b plus t of b minus o a. Okay, and then we can do modulo the inside. Okay, modulo, this is 1 trillion, right? 1 trillion mod 1 trillion. Oh, okay. So the problem now is we have to run it. So actually, I haven't set up GCC for Windows, and the ideal setup if you want to access all of the tools, C tools, as C and C++ tools, is have a Linux environment. So I used a virtual machine here. Okay, so I have my GCC here. Okay, so and the problem is, how do we transfer this file to the virtual machine? I use a service called piratepad.net. So it's basically a text transfer, okay, from computers. So this is hooked up to the internet. So I'll just, oh, let's switch to the virtual machine. Okay, so I'll just copy it and then run gi. Okay, and then paste it. Save. Okay, now server. Let's see. Oh, wait, what happened? Okay. Next, we compile it. So this is our program. No, not this one. Okay, so we compile it. Since we do mathematical functions, we include the switch lm. Okay, so we have an error. So line 12. Oh, yep. Ah, line 4, line 12 expected 12:38. Okay, something wrong in line 12. Okay, forgot this one. So again, no, virtual machine is kind of slow. So next, 16 and 10. Oh, didn't return something. Yeah, you have to return something. Okay, then run again. Oh, 17. What is wrong with this program? Oh, forgot. Mhm. The, the response of the virtual machine is kind of slow. So okay, another error. 21.5. Define the reference. I include math.h, right? Forgot. How do you run? Is it ml? lm? Oh, okay. I'm not an expert in C for Linux. So this one will produce a outside. So 12.3. Oh, and C should be this one. Okay. So we have 12.3. So it's 7. So we have to send back the correct code for this one. Okay. So actually, for the parts that have corrected, okay, it's shaded in a different color. So this is really a nice tool. Okay, so that's it. And overwrite our solution, and then submit. So we use C here. Okay. Huh. Whoa. That's weird. Do we have a leak somewhere? So long T O size. Do we have a memory leak somewhere? A of size. This is 1 billion, right? It's weird because it worked in the compiler. What's wrong with this code? This is the corrected one, right? That's weird. We have a memory leak somewhere. Hmm, it's weird. Personal exam. It's weird. It's weird. It runs on my machine. Let me figure out. Hmm. Where's the problem for this part? Where's the problem? Okay, there's something wrong with scanning. This one would work. What's wrong? We're missing one line. The joys of programming in C. Okay. Why did it work? Why did this work? Okay. So we are correct. Okay, so let's take a look at the code. Okay. So for each pass, let's try to print it. So as you would notice in the note section of the NOI guys, so for Bob's problem, we have two algorithms which runs in ON log n, which is a recurrence relation, and ON. Uh, okay, what if we have a bigger value, like 100? Okay, let's take on a denomination that is simpler, like this one. Okay, so the explanation for this algorithm provided in the Rosetta source code, in the Rosetta code, is that um, we have initially, let's say, 10, 10 values for n. Okay. Actually, if you take a look at this, okay, for the last row, this is the answer, 9828 for inputs 102. This would be the number of ways in which to, in which the change can be expressed for values 99, 98, 97, and so on and so forth until the value 1. Okay, so essentially we record the previous values for n minus 1, n minus 2, and so on and so forth until it reaches 1. Okay, so in simple form, let's assume that we have the denominations 1, 2, 4, and so on and so forth. Okay, if we only have let's say 1 as the denomination, how would how many ways can we express the following values in terms of uh, coins 1? So for 1 it's just 1, 2, 3, 4, 5, 6, 7, 8. These are all 1 because we're just using one denomination. Next, what if we use the denomination 2? Okay, so what if we introduce 2 to the system? So for values 1, it's still the same because it's only 1. For 2, it changes though, because although we express this one as 1, we have a new value which is 2. So this should be 2. Okay. 3 is just what? 1 plus 2, right? So this is just the number of ways in which we have 1 and then we add 2 for this one. Okay. For 4, this is just the number of ways in which we have 2. So we have this one, 3, right? For 5, it's 3. Okay. The number of ways we can do change in 2. Okay. For 6 is what? 4, 4, 5, 5, and 6. Okay. Next, for 4, we have what? For values 1, 2, and 3, this is just 1, 2, and 2. Okay. Next, we have 4. Okay. This is just 1 more than this value, which is 4, right? Next, 5 is just what? Number of ways we change this. Okay. So this is what? Okay. 1 more than this. Okay, so 4, 5, 5. Wait a minute. 5 is uh it's just this one plus this one. Okay. 6 is what? 2 and 4. Okay, so this is 6. So this is just 6. Okay. 8 is what? This is already 2, right? Or 4 rather. Okay, 4. And then the previous value is 5. So this is 9. And then this is 9. And then this is what? 10 and 6. This is 12. Is it 12? Yeah, 12. Okay. So essentially, the pattern for this series, I'm sorry if the explanation is kind of complicated. It's just the previous value, okay, of the array, so the topmost part, plus the index, okay, that is less than the value of the currency. So let's say this is the first pass, second pass, third pass. Third pass has a value of 4. So we get the previous value and then we minus it by the index of 4. So 10 minus 4 should be 6. So we add this one and this one. Okay. I guess this is just similar to the recurrence relation, this one. F of n minus 1 plus n minus k if n is greater than 0 and n is divisible by k, or f of n is equal to f of n minus 1 if n is not divisible by k. But actually that's the pattern. Okay. I'm sorry if this one is kind of complicated because most of the people who will be viewing are high school students, but you could also study this one. Okay. And you could also study this one provided by Rosetta code. Okay, so brackets Rosetta code change coin. So actually it's a change for $1. Ayan, count the coins. Okay. Okay. So the elegant version is the JavaScript part. You could study the recursive part. Okay. Okay, so I'm sorry if the explanation is too complex. So that's for Bob's Prob. Okay, so thank you for watching.